Thanks everyone for joining, and welcome to the it's actually the fourth Clean Code Nugget. I know it says 3 there, but that's a typo. Um, this is the second in a series of presentations on testing. And in this presentation, we'll have a quick recap of Clean Code and its relation to testing. We'll look at the process of adding tests to untested code, have a look at an example of doing this, and then do a quick summary of what we've looked at. And that's going to be it for this presentation. Trying to keep it quite focused. So a quick recap of Clean Code. I'm sure everyone knows what we consider Clean Code to be. I'm not going to ask someone to come up with their definition of it. I think we've done that quite a few times now. Basically, easy to understand and easy to change. This relates to testing because if we have no tests for our code, then it's not easy to change, as we don't know when a change to the code has actually broken the required functionality. Therefore, we really need to have tests in place on our code to make it easy to change. But what do we do if we have untested code and we want to add some tests to it? Personally, when you come across this situation, when you're taking over someone else's code or you've developed some code that doesn't have tests in it, it seems like a huge task to start off with, and it's quite difficult to know where to start. But thinking about this, in our previous Clean Code Nugget, we had the simple definition of a test, where you have a system under test, you have some inputs to that, they're known inputs, and they should produce expected outputs. And when you run the test, you create some outputs and compare those to the expected outputs, and the test either passes or fails. And we can use this as the basis for actually developing some tests, because if we know a set of inputs and their resulting outputs, then we can use this to define an initial system test for the SUT. You know the inputs, you know the outputs, and therefore you've got the basis of a simple regression test here. If the regression test passes, then you're reasonably confident that the SUT still has the same functionality that it did before. However, we do have a problem if we're just using the standard system under test. Our outputs are normally written to something like a live database or a file system, the live file system. And if we then use this for a regression test, then this is going to cause us problems, because our live database or file system is going to get polluted with a lot of test results. Therefore, we need to make some changes to the SUT so that it records results somewhere else. And there is a process that we should be following to do this. It's got a number of different stages in. And in summary, the first is to identify a useful set of inputs and the outputs for your SUT. We then need to make a copy of those outputs. This copy may not be in the same form. For example, the normal outputs might be in a database, but it may be easier to have the test work on some text files, as they're easier to compare and they have the benefit of being quite easily read by a human. Also, by making a copy, you're separating the test data from the live data, which is a very good thing to do. We then, at step 3, is to make the minimum changes to the SUT to allow it to create the test outputs in a form that can be compared to the expected outputs. This refactoring needs to be done very carefully, and we'll go through an example of this in a few minutes. Once we've done that, we can then actually create our test, and that test will be passed the identified set of inputs. The SUT will then create some outputs, which we then compare to the expected outputs, and that'll tell us whether the test has actually passed or failed. We then might want to do some tidying up at the end. For example, if the outputs are text files, you may want to delete them from the file system to keep them happy. However, and keep it tidy, sorry. However, you do need to be careful that the test needs to make it clear why it failed. And sometimes, though, any output files that you've got are very useful to be able to understand what actually went wrong in a test. So be careful when you're doing that tidying up. Once we get to that point, we have a regression system test in place, and that gives us some confidence that the system is doing what it should. We can increase this confidence by repeating this process until we have coverage of all of the different parts of the functionality of the system. So, for example, if you're running your system on some input wind data, then you may want to use datasets that come from a standard resmast, but you may also want to include a set of data that covers instrument replacement or an RSD site or things along those lines. And it can be quite difficult to decide when to stop this process, to decide when you have acceptable coverage. And the two things that you're comparing there are the effort of actually creating and maintaining those tests and the time taken to run them against the benefit of actually adding more tests in. So it's not necessarily a very simple decision to make. And then finally, once you've gone through that process and you have your acceptable coverage, then you can go on to refactor the code that you already have to improve the quality of it. And this is going to almost certainly include adding some other level of testing, almost certainly unit, but maybe integration or system testing. So that's a very quick introduction to the process that we should be following. Does anyone have any questions at this point? I'll take that as a no then.
I guess one quick note is you can give a tidy up at the start of that process as opposed to the end. And
That's true.
Then the outputs are still available, sort of like when it crashes or whatever.
Yep, that's a good point. So instead of tidying up being here as the last step of creating the test, as you said, you can have it as the first step instead. So if there are any output files that are left over, you might remove those, or you might do some other steps. Yeah, that's a good point. So anyone else got any comments? Okay. So let's move on to looking at an example of this process. So we have, in the UK, we have a site selection web app. And as part of that, we display details of land ownership to the user. This displays the details that we get from the land registry, or we purchase from the land registry, so that we can easily see who owns which parcel of land and other details on that ownership. We purchase the data from the land registry, and the data comes in the form of two related data files. The first is a shapefile providing the polygon data, and the second is a CSV file that contains the landowner details. We have a land registry upload Python tool that takes those two files, combines the data together, and adds it to the required geodatabase on our system so that the data can be shown on the web app and in other GIS tools. Now, unfortunately, when we took over support for this tool, it contained no automated tests at all. So we had to go through the process that we've outlined previously, and that process was as follows. So the first step is to identify a useful set of inputs and related outputs that the SUT can then deal with. Luckily, when the tool runs, it creates temporary files in a specific location, and these temporary files aren't tidied up on a regular basis. These files contain a date and timestamp so that we can see when they were produced. And you can see here we have a number of them that will all run on the 25th of September at different times. And we can take one of these files and create an output text file from it. This is the data that's in the CSV file, and in fact it's actually in the temporary file here, and that is a combination of the details of the actual shape itself and the title number, the proprietor, the person who owns the land, their address, the tenure, and other details like that. And in this file we can see that there are title numbers that are included. Now the data that we receive from the land registry is stored in a specific inbox folder, and what we can do, or what we did in this case, was we searched through all of the CSV files in that folder to identify the CSV files that contained these title numbers. And by doing that, we could identify the input files that were the source of the temporary files, and therefore these are the input files that relate to this output file. So we now have a set of input files and the related output file from them. So we have completed step one. Sorry, I didn't mean to click on that one. And in fact, we've also completed step two because we've taken a copy of that data and we've created our own output file. So we've now completed the first two steps of our process. Moving on to step three, and this is where it starts to get a little bit more difficult. I will say that I'm going to be showing some Python code on the screen here. Hopefully it's still going to be readable to you, but if it isn't, then please let me know and I'll try and explain any relevant details. So we need to adjust the tool to allow a test to output the combined CSV and shapefile data into a text file rather than the database table that's used in the live data. Now, looking at the Python code, here's the constructor and the other public function to that tool. The public function is this upload to database one. And if we look at that function in a bit more detail, you'll see it's broken down into a number of different steps. To give you an overview of that, the first of these creates a table of data which contains the data from the CSV file. We then create a feature class from the shapefile. We add the required geographic projection to that shapefile. I'm not going to go into details of what geographic projections are unless anyone really wants me to. The fourth is a check. It's carried out on the shapefile to make sure each of the polygons has the required data within it. We then add the CSV file data to the feature class polygons using the title number as the key. And then finally, we take that feature class data and add it to the geographic database. And it's this final append feature class to database function that we need to change. The details of this function are shown here, but they aren't really relevant because what they are doing is they're using the ArcPy functionality to write the details out into a separate geodatabase. But in the test, we're not actually going to be doing that. So how do we actually change the system under test to create those different test outputs? what we did is to take the functionality from that append feature class to database function, and we put the same functionality into an append function on a new class. That class is called append feature class to database. So we're moving across that functionality as is, making the minimum number of changes that we possibly can. The main changes being that some of these values were member variables on the first class, and we're now changing those so that they're actually passed in as input parameters to the function. Now, once we have this class, we can then make changes to the tool, the main class for the tool itself, which is the LanderEdge DB uploader. And what we're doing here is we are providing an optional parameter to the constructor of this output feature class instance. This is optional, and if it's not provided, then we're actually going to create an instance of the append feature class to database class. But if it is provided, then we're going to save it into this output feature class instance member variable. And this is using a process that's called constructor injection. We'll come on to mention that a little bit later as well. If anyone does have any questions or any confusions, if you want me to give any more details, then please let me know. Now that we've actually got that output feature class instance member variable, we can change the append feature class to database function that we started off with. We can now change that so all it does is it calls the append function on that member variable, passing across the relevant details. So when we run the tool in the live environment, the call to the constructor will not provide this optional parameter. So we're going to create an append feature class to database instance, and then when we call this append feature class to database function, it's going to call that append function. And as the append function of this instance has the same functionality as before, it should perform the same actions as before. So when we actually run the test, we want to save the feature class details in a different way. And to do this, we need to create a new class. Unfortunately, it's got this terrible name that everyone should identify as being a bad name that we should improve on. But it starts off and it has one append function. Similar to the other class that we just created, it's got the same input parameters. And all this does is it calls an internal function. And the internal function is shown here. In summary, what that's doing is it's taking the details of the feature class that's been provided and saving it into the actual contents member variable. Oh, sorry. So this actual contents member variable is then containing the details of that feature class. We're also adding a second public function to this new class, the file contents matches feature class, where you're providing an output file path, the expected output that you've got. And what this function is doing, it's comparing the details of that expected output file path to the details of the actual contents and checking to make sure that they're providing or they do contain the same details. That's actually done by calling this compare expected and actual lines, which is just going through and doing some very simple comparison, but it's also printing out some important details of what differences there are if it finds a detail if it finds a difference. So we're checking to see, for example, we may have a different number of items on the line. We have a mismatch. If we have a mismatch at a certain point, then we'll print out the details of that. And we're doing separate comparisons depending on whether the values are float values or just standard strings. So once we've got that in place, we can actually create a test to use that functionality, and we'll follow the steps that we laid out earlier. We're going to start off with using the identified set of inputs. Then we're going to run the SUT to create the outputs, compare those outputs to the expected outputs, and then do some tidy up. So here is the test that we've written to do this. It uses the inputs that we've identified, the shapefile and the CSV file, and it then compares the details. So you can see here that we're creating an instance of the class that we've just looked at, and we're providing that test comparer into the constructor for the LandRegDB uploader, and then we're calling the upload to database function. So if we're looking at the AAA pattern that we discussed previously, the code before here is all arranging. This line here is doing the actual act, running the SUT, and then the final element of it is the assert part, where we're calling the file contents matches feature class on the test comparer to make sure that the feature class contains the same details in the expected output file path. In terms of the tidying up, we do some of that, but this is mainly because we need to have some geodatabases in place, which is to allow the ArcPy code to run. And we're actually doing some setup before and afterwards, and afterwards we're doing some teardown to tidy up. Does anyone have any questions on that or comments? No? Okay. So now what we do have is we have one regression test. So our next step would be to keep adding the functionality until we have sufficient coverage. In this case, the functionality of this tool and the things that we really need to consider are whether we have multiple owners for a particular title and whether we have multiple polygons for a different title. And this might be where there's a parcel of land but there's a road running through that parcel, in which case that parcel will be split into two separate polygons, each having the same title number. Now in this case, the example case that we've chosen does actually cover both of these cases. We have multiple owners for a particular title number, and we have multiple polygons for a particular title number as well. So we don't need to add any further cases. If this wasn't the case, then we'd repeat the process until we did have acceptable coverage. So our final step in the process is to start refactoring the code to make it cleaner. And there are some general guidelines for this refactoring. So your time is important, and you don't want to be refactoring code unless you really need to. So you should only really refactor code if you're debugging or reviewing it and it's not easy to understand, or someone's actually found a bug in that particular piece of code. So don't just add new tests. Once you've got the regression tests in place, your code is tested and your functionality is tested. So only start to refactor the code when you need to. It's also important that when you're making changes, you don't make huge changes in one go. You want to try and break your changes down into smaller steps. For example, if you're moving the code into a new functional class, as we did earlier on in this example, then you move the code first with the minimum number of changes to get the code working. Don't try and change the way the code works at the same time. You can always go back to do that in a separate step later. And really, very importantly, whenever you make a change, rerun your tests. This is really important because it's going to help you identify when your code has changed. If you make, say, a dozen changes to your code between your test runs, then you then find the tests are failing, you've got to go through those dozen changes that you've made and find out when the tests stopped working. So it's important to run your tests as often as you can to be able to identify any problems that you're introducing. Now, assuming that your code is source controlled, and if anyone has any code that isn't, you should seriously consider adding it to source control. You should check in your changes often. This will give you and others a better idea of what changes were made, why you were trying to change them, and when things went wrong if they did. It's also good practice to not check in code if you have any failing tests. If you are refactoring code, consider creating a new class rather than adding more functions to an existing class. It's much easier to understand small amounts of code and code that is focused on a specific task or objective, and that's why we use classes in OO. And the example is of the append feature class to database class that we created in the example. But this then leads to another problem. When we have lots of classes with specific responsibilities, how do we get our main class to call these classes? And this goes back to constructor injection, which we saw an example of earlier on, when we were passing the instance into the constructor. That instance is then saved as a member variable and can then be used further on. The main advantage here is that you can then provide different functionality into this main class, and if that separate class contains the same interface, then you're not changing the functionality of the main class itself. And constructor injection is quite a powerful design pattern that I definitely recommend. One other thing to consider is when you've got code that's communicating with a data source or a source of information, be it a database, an API, or a file system, it's usually a good idea to have a separate class dealing with all the communications with this source. This has a real benefit that you can then replace this class when you're running the tests that have and you can plug in a different data source, and then this goes back to the example where we had the different class so that we could provide the outputs into a text file rather than into the database itself. So that's some general advice about refactoring. Does anyone have any comments on that? Okay. So going back to our example, how do we do this? Well, it's going to depend upon what needs to be done to this code. Is there a bug to fix? Do we need to add some more functionality, or can we not understand some of the code? In this presentation, I'm not going to go into the refactoring of this class because firstly, to do that and make it understandable, it's going to take a long time to show anything useful. It's also going to be quite difficult to show that code on the screen and make it readable to you. And finally, we haven't actually done that much refactoring of this tool because we've got the regression tests in place and we haven't needed to make any other changes to that code. However, having said that, there is one thing that you do need to bear in mind. The functionality for this append feature class to database function and the class that sits behind it is going to be very difficult to test, as it's tightly coupled to the structure of the live enterprise geodatabase that we have behind it. And in this kind of situation, we have a couple of options. Firstly, we could spend quite a lot of time creating some automated tests, which would require us to create the enterprise geodatabase structure behind the scenes and test that functionality. Or our other option is to accept that this code is very hard to automatically test. In this case, what we would do is to label the code clearly so that anyone who comes to it later on knows that it's not automatically tested, and therefore if you are making any changes to it, there is added risk to it. Now, this isn't the ideal option, but it may well be a pragmatic choice for you. So that's the example. We've looked at that example, and that's pretty much what we've got in this presentation. In terms of a summary, we've looked at the process of adding tests to untested code. We go through, identify a set of inputs and their related outputs, take a copy of it, adjust the system to create these different outputs, then create a test that goes through the process of using the inputs to create the outputs, comparing them, and carrying out any tidy up, either at the beginning of the test or at the end. We then repeat this process until we've got acceptable coverage, and finally we can then go on and refactor the code to improve its readability. And when we're doing that refactoring, only refactor code when you actually need to. So when you've got a bug or you don't understand it and you need to make changes to it, you want to make small incremental changes, rerunning your tests after every change, checking your code changes often, creating new classes when that's appropriate, using constructor injection to provide those new classes to other classes, and use separate classes for communication with data sources such as databases or APIs. So that's it for this presentation. Does anyone have any questions on this?